Morning, observatory fans. No, of course this does not go away, because I don't want my children growing up on a planet where the reasons for working out the speed of light are wrong from the very, very beginning. When something is wrong from the very beginning, the end, who knows where it goes? Now, old Roemer, out of the ballpark ridiculous, okay? It could be an oversight. This could be nothing more than an oversight, right? The telescope. When you look through a telescope at an object, it doesn't matter where you are. You are going to see the object in the same light all of the time. That is what the telescope is for. That is why Roemer used a telescope, so that he could see Io and Jupiter as they were. And by seeing Io and Jupiter as they were, there would have been no delay, because it was being observed through a telescope. With capital letters, a slam dunk. Now, we just so happen to find number 2, James Bradley. Now, this is incorrect knowledge. It should be retracted. Should it not? I think it should. The more intelligent these people are, right, the faster they should realise the mistake they've made. Oh no, it's a telescope. He's right. It's wrong. What does this mean? And they should be picking up the cars and building the houses again, kind of a thing. This is wrong from the word go. If something is wrong from the word go, how can it be left to continue? Just look at this.
Second. Now it's fast enough to go around the world 7.5 times in 1 second. But when did we discover this? And how many scientists have the means to measure that speed? Well, stay tuned. This video will look at some of the history behind measuring the speed of light.
High school physics explained.
There were a number of views about the nature of light, but they did lack experimental evidence. Some, like Pierre Cassini, thought that light was travelling in bits, or what he referred to as corpuscles, whereas others, such as René Descartes, believed that light travelled pretty much like the waves on the ocean. There was the idea that light travelled with a certain speed. In essence, it was thought to be instantaneous, so there was no real way to actually measure the speed of light. So the first key experiment is the one made by a guy by the name of Olaf Roemer in the 1670s. Now, Olaf Roemer was a Danish scientist who went to the observatory in Paris to observe the eclipse of one of the moons of Jupiter, called Io. So what I've got here is a diagram that is actually from Olaf Roemer's work that shows the path of the Earth and the path of Io, Earth as it moves around the Sun, and Io as it moves around Jupiter. And all I've done is just add little icons here of the Earth, Jupiter, and Io to help us understand what's going on. So he was interested in the eclipse of Io. So Io moves around Jupiter like so, with a known period of around 42.45 hours as it goes around. Now, how was he able to measure that? Well, if you were to, let's say, be in this position, you would see it appear out of the shadow here, and then go around, and then when it next appears out of the shadow, that will give you the period. Now, if he were to measure it on the other side of
Wouldn't matter.
of the Earth around the Sun, then he would also look at the eclipse as Io entered the shadow, and again as it again entered the shadow the following
through a
time.
telescope.
Throughout his time of measuring, the Earth, of course, is moving around like so.
It doesn't
Sometimes
matter.
it's measuring the period around F, and a lot of times it's around G, and so forth, L and K.
It doesn't matter
If he
where
was to
planet
miss
Earth
it, he wouldn't
is.
be able to see anything.
He's
because
looking
Jupiter would be in the way.
through a
Similar issue
telescope.
is if the Earth was between K and F, then the Sun basically is in the way, and so he wouldn't be able to measure the period of Io at all. But the problem that Olaf Roemer discovered is that he found that his values for the period varied. They weren't always 45.45
doesn't matter where it goes.
Sometimes they were smaller.
People have to
sometimes
see
they
this.
were
You
larger.
have to understand
and
this.
it turned out that they were larger when you were at position F and at position K, and smaller at position G and at position L. And what he was able to infer is that the light that is travelling from Io to the Earth, well, it has to travel a longer distance to get to K. And that was the reason why
Not
there
if
was
he's
delay.
looking
The light was
through a
taking longer to
telescope.
get to K than it was, let's say, at L, and similarly over on the other side. So the first thing, and really critical thing, is that light is now finite. That is, it has a speed. It's not instantaneous, because clearly light has to travel a certain distance in order to be perceived, depending on where you are around the orbit. So that's the first thing. And the second thing he was able to do is to say, well, I can work out the delay from the maximum distance. And the maximum distance is 180 degrees. In other words, it's at E. Now, he couldn't actually see Io, but
They continue to repeat the delay, and I continue to say there can be no delay when these things are observed through a telescope. It is impossible, it is illogical, and it does defy common sense, okay? These people, they come across as intelligent. Like I said before, it should be a quick, instant switch. Whoa, I'm sorry, this must be wrong.
in mathematics, he was able to determine that the delay here from there to there, in other words, the maximum delay you'll ever get is 22 minutes. Now that means that it took an extra 22 minutes for the light to travel from this position here to this position here. And if you know the diameter of the orbit, you can now work out the speed of light. Now, Roemer didn't work that out. Christian Huygens used Roemer's results and determined.
And now we've involved Christian Huygens. So we've jumped from Galileo to Roemer, then it's going to be Bradley, right? This thing, it started wrong, okay? You have to understand something here.
The speed of light using this data to be around 212,000 kilometers per second. Now that is, of course, significantly lower than what we do know as the speed of light today, but that's predominantly due to the fact that they did not have an accurate measurement of the diameter of the Earth's orbit around the Sun. So that's still pretty good considering that we're...
So now, here we have somebody else saying, which we've heard before, that he didn't even have an accurate reading distance about Earth's orbit around the Sun. So not only does he not know exactly what the distance is between Earth's orbit around the Sun, there are claims being made that he observed a delay in the time that it took Io to orbit Jupiter, which is clearly wrong. He would not have observed any delay because he was using a telescope.
Dealing here with scientists working in the 17th century. Now, Roemer presented his findings, but many were skeptical, and it wasn't until 1727, with the work of James Bradley, that he was supported. Bradley was an English scientist who, in 1727, also used astronomical methods to determine the speed of light. In this case, he examined the position of stars. So what did James Bradley do? James Bradley was looking at the...
So now we have arc minutes and arc seconds. Do we remember? Do we remember? 1 degree. 1 degree has how many? How many was it? That's right, 60 arc minutes. And in each of those 60 arc minutes, there are 60 arc seconds. That turns out 3,600 units in each single degree. Alexa, what is 60 multiplied by 60?
60 times 60 is 3,600.
3,600. Alexa, what is 3,600 multiplied by 360?
3,600 times 360 is
1,296,000.
1,296,000.
That's how many sections, that's how many degrees we have to play with now. Not actual degrees, but that is how many slots. We have 3,600 slots to pick from in 1 degree.
Positions of the star. Now, you all look up into the night sky and think the stars are in the same position, but they actually do vary slightly. And that's simply because of an issue called parallax. Now, the Earth, of course, moves around the Sun like so over 365 days. That means if you were to examine the position of, let's say, a particular star, its position will be different depending on what time of year you are looking at. If I were to move the Earth 6 months later, then the position of the star in the night sky would be just slightly different.
But it is also general knowledge that the stars are moving as well. So you cannot take accurate measurements from a planet, right, that is orbiting a sun, that is orbiting the center of the Milky Way, the galaxy, the Milky Way, and compare it to some star that is orbiting something else, because there are too many variables again. This whole thing is ridiculous. This whole thing is just...
As a result, if you were to watch a star over the period of 365 days, you would find that it actually moves in a small circle. Now, what James Bradley predicted is that if you were to, say, see the star in this position in December, then you would see this position over here in June, and similarly speaking, you would have the intervening months in those two positions.
And of course, back in 1728, we had all of the equipment in the world to do these observations. I mean, I've got 1 degree to play with, and I've got 3,600 sections to pick from, and I'm going to go for, I think, with all of the info and all of the instrumentation and the electrics and measuring devices that I have, I'm going to go for 2 arc minutes.
But that's not what he got. He found that there were slight delays, and as a result, he was able to infer that there was a delay, a change, simply because as the light was travelling to the Earth from the star, then the Earth would move. And
Please don't tell me that you thought that made sense.
a delay, a change, simply because as the light was travelling to the Earth from the star, then the Earth would move. And so, because the Earth is moving, once the light appears, it's actually coming from where it was at that time. And then what he did was mathematically determine the difference in these angles. Now, these angles aren't very big. We're talking about very small angles in fractions of a minute. Using this concept called stellar aberration, that is, the light is travelling towards the Earth, but the Earth is moving at the same time, you're getting a difference in where the star is supposed to be to where the star is seen to be.
Now, no comment is better.
He was able to determine the speed of light, considering that the Earth's speed has a particular value for v. And as a result, he worked out the speed of light to be around 303,000 kilometers.
Now, why did Roemer waste his time? This guy looked at 1 star. 1 star! Light's coming this way. The planet's moving. So now what? Are you looking up back at that same star? Or is it this now when we look at the displaced and perceived position? So is it there or not? What are you looking at? Are you looking at another star? The perceived displaced position star? Or the actual position star? Or in that 6 months, have we lost it? And it's a totally different star.
Kilometers per second. Now that is particularly good considering he was using only astronomical means by measuring the deflection of the stars of where they.
Now what we have to understand, it was 20 seconds, it was 20 seconds arc, it was a third of a minute. So it was a third of a minute. There are 60 minutes arc in 1 degree. It was a third of one of those minutes, so that's 180th of a degree. I think that might be right. It's straight off the top of my head. So when you see these angles like this, that's get the protractor out. That's got to be close to 45 degrees, right? What we're talking about here, right, is a third of 1 degree. Looking up at the night sky, picking out a star and saying a third of 1 degree, how it's moving, speed of light is this. People, is this how we think now? Is this what we accept?
Fortunately, in the way that we're appearing today. Our next scientists did not use astronomical means to determine the speed of light, but what is referred to commonly as time of flight experiment. And in 1849, Hippolyte Louis Fizeau developed a really cool experiment using mirrors and a very good cogwheel to determine the speed of light. So here we have our diagram that represents Fizeau's experiment.
We have a simplified diagram here, because we don't want to confuse you, right? So we're going to keep it simple, because his was a lot more complex than this. Back when there was no electricity, and he was just about to measure the speed of light, okay? But they've kept it simple for you, okay?
Light source over here. Then what we have here is what we call a half silver mirror. And what happens is that the light would pass through this half silver mirror, through separation in the cog, and then strike the mirror over here. Now then the light, of course, would return via the separation of the cog, and then it would go off to the side half silver mirror, and you would be able to observe the light passing through this time. Now the cog, of course, is spinning all the time, which
The cog, of course, is spinning all of the time, okay?
means at some stage the light would pass through the gap, but then be blocked by the time that the light returns. Now here is a diagram that also looks at the same situation from a two-dimensional perspective.
Because when you see in something like this, you need the two-dimensional diagram to assist in the explanation of the totally absurd, illogical, and obviously impossible.
So let me repeat that. This thing is turning with a particular frequency. The light, as this turns, is passing, going down and back, and this distance is a certain distance we call.
And of course, the light that we are talking about is coming from a distance of 8 kilometers when there is no electricity, right? So this light is a lamp or a naked flame or a lamp, right? Or a naked flame or a lamp or 8 kilometers. A beam of light before there was power picked up a tooth. Listen, I'll stop right now. I'll just let this continue.
L. And that value, in terms of what Fizeau did, was a value of 8,630 meters. So how was he able to determine the speed of light using this setup? Well, let's break it down. The first thing you need to appreciate is that the speed of light going to and fro is simply equal to...
Yeah. That is 8,630 meters. Right? That's 8 kilometers. You do understand this. No power. There was no power. There was no electricity. That should be it, really, but no. We love the story, yeah?
twice the distance because it's going there and back, divided by the time it takes to go there and back. So how is time related to the spinning cog? Now this cog had 720 teeth here.
But, it doesn't seem to have 720 teeth there, does it? So why would you not show us 720 teeth there so we can see what it would look like if there was 360 teeth on this side and then 360 teeth on that side? Because then we could see how ridiculous this is, right?
He had a friend who was a clockmaker and was able to produce a really accurate cog with 720 teeth. The speed of the cog,
Really good clockmaker.
is going to be equal to simply 2 pi rf. That is, the 2 pi r is the total circumference of our cog multiplied by the frequency. But the distance between this cog here and this cog here is simply equal to the total circumference divided by the number of cogs, which is going to be n. So therefore, our total time going as this spinning around is simply equal to the distance, that's this distance here.
See, but it's simply this, and it's simply that, and it's just this.
Here divided by the velocity, which is this velocity over here, which means you end up getting a value of equaling the time 1 over nf. But Fuseau was looking at the time that goes from the blocking the view to seeing the view. So he was getting the right speed, not for this distance here, but only half that distance here. So therefore the time that he was interested in was not 1 over nf, but ended up being 1 over 2nf. So now we...
And remember, we're talking 720 teeth, aren't we? 720 teeth. So that's 360 each side. So it's just NF, 2NR or something.
have the total time that Fuseau used, and that's the time that we need up here. We get now the speed of light is equal to 2L divided by this 1 over 2nf.
Oh,
and that,
of course it
is equal to 4lnf.
But the thing is, people are just nodding, thinking that they understand. You know, nothing's understood here because nothing sensible is being explained here. What you are being taught here is incorrect knowledge, right? That's the worry, but the worry is also that so many people just listen to this stuff and believe it. And this is the world we live in today.
Now, Fuseau had a length of 8,630 meters. He had, of course, 700.
Oh no!
LNF. Now, Fuseau had a length of 8,630 meters. He had, of course, 720 teeth. And the frequency that he ended up getting was 12.6 Hertz, or 12.6 revolutions per second. And as a result, he calculated the value of the speed of light as 313,000 kilometers per second. So this is the first real experiment to determine the speed of light by what we refer to as the time of flight methodology. Now, it's clearly not super accurate, but
We agree on something.
reasonably good in terms of working out something that is not astronomically based. Fuseau's experiment was not accurate, so Foucault set about to improve Fuseau's experiment by replacing the cogwheel with a rotating mirror and reducing the path length from around 8.6 kilometres to about 20 metres, though he mainly did this because of technical limitations. So here we have Foucault set up, And in Foucault's case, we have not a rotating cog, we have a...
This is a first for me. I haven't got to this stage yet.
rotating mirror. And so what happens is that this mirror spins, and as light travels down through this half-silvered mirror and bounces back again, the light would reflect at a different angle depending on the frequency of the spin here. And as a result, he was able to determine the angle between the light source and also what he saw, and based on the number of spins that he was getting and what the path length he had here, he was able to work out the speed of light. So let's have.
And again, this is like listening. There's just no specifics, right? And this is what everybody, these are the links that people were sending me. I wasn't even looking at anymore. What are you understanding here, right? There is nothing to understand here. It's just numbers and distances and words and revolutions, and nothing means anything. And it always comes down to, and then he was able to work out the speed of light because of this. There is never a specific number, a specific reading, a specific amount of anything. It just always ends up as, and then he was simply able to work out the speed of light because...
Let's see how that works out. But we know that the time is still equal to 2L divided by C, and this is the value he is interested in. And so what is the time? Well, the angle that he actually determined over here, remember he measured this as to the angle, so he was able to work out the angle here. That is equal to omega t, and that's simply circular velocity here. So omega is angle over t.
Simply
so
circular velocity,
here, which is the time here. Now, that means we have t being 2L over c. So we've got 2L over c multiplied by omega. Of course, he had the angle, so c is equal to 2L omega over theta. Now, the value he ended up getting was 298,000 kilometres.
So the value he got was 298,000 kilometres, right? But how? A few letters here and there, division, subtraction, and boom, 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 right? There is never, ever a specific number. They never go from one thing with a dead set, confident, this happened here, and we therefore got 420 millimeters per second, or there is never anything specific, right? You're being led down a garden path, right, by the hand, and everybody's going to be walked into the pond.
Per second. So his value of 298,000 kilometres was very good. Good enough, in fact, that in subsequent experiments, which involved shining light through moving water, he was able to conclusively show that light travelled slower in the water. Albert Wilkerson used the same setup.
Now, bit of water, right? Now we're going to do the water. I wonder if it's the same aqueducts. The pyramids, the stones from the pyramids were pushed down. Maybe they went to Egypt and they, just thinking ahead maybe. I'm going to leave it, I think, because...
Foucault, but he improved on it, basically by improving the objects and increasing the baseline considerably. And in 1883, he published a value of 299,800.
3 years we've had power. For 3 years now, 1880.
And 53 kilometres per second, give or take 60 kilometres per second. Now, it was about this time that James Maxwell, in 1861 in fact, published his theory of electromagnetic waves and determined the speed of an electromagnetic wave at the value of...
Now, an electromagnetic wave worked out before there was electricity. So all of this is this Christian Hegelian as well, they worked out waves, right? All of this stuff that light is made from and how it reacts, how it behaves, what it does, before electricity, before the light bulb? How? One question. How? They didn't have a light bulb. All they had were open flames, lanterns, and the sun.
300,000 kilometers per second. Now, this aligns so well with the speed of light evidence that he was able to state that light was a form of electromagnetic wave. Now, I'll discuss more on Maxwell in another video. In the last 100 years or so, there have been a variety of experiments conducted to further improve the precision of the speed of light, with experiments determining the constants in Maxwell's formula, the use of standing waves in microwaves, and the use of lasers and cesium clocks. The precision now is so high that we are able to define the unit of distance by it. And the definition of the meter is now defined as the distance light travels in a vacuum during the time interval of 1 over...
That's not.
299,792,458 of a second. So that makes the speed of light exactly 299,792,458 meters per second in a vacuum. So our understanding of how light travels has developed remarkably over the last few centuries, getting ever-increasing accuracy as technology has improved. And in the last few hundred years, we've learned so much more about the nature of light. But that's the subject of our video. Well, I hope it...
Coffee and some breakfast post this.
You need to wake up, Pete.